Welcome to Spring LIB.
For this problem, we have been given 8 lists of integers, and we have been tasked to find a simple formula or rule that generates these sequences. Once we have that rule, we need to use it to find the next 3 terms for each of the sequences. They are not dependent on each other, so we're just going to take them one at a time. Okay. So first, we have a collection of ones and zeros. Well, we're alternating between them, and it looks like every time we get to a number, we use it one more time. So we have 1 of each, 2 of each, 3 of each. Now we are on to 4 of each. So our next 3 terms are all going to be ones because we need to get 4 ones in. Now, for all of these, we could certainly go farther. If I kept going, I would now have 4 zeros. But since we only need to find 3, we're going to be stopping right here. Now, next sequence. Obviously, increasing integers. It looks like we're hitting every integer in sequence, but not the same number of times. If I look at the odd numbers, each of those is coming up 1 time. If I look at the evens, each of those is being recorded twice. So it looks like odds are once and evens show up twice. So my next 2, 9 is an odd, so I'd put that on once. 10 is even, so those would be both 10s. Okay, next sequence. Well, we have every other term. Looks like it's a 0. So this is kind of like the last one. We had 2 interwoven. The odd number of things did one thing, the evens did something else. This one, it looks like every even number in my sequence is going to be 0. So it looks like that term should be a 0 as well. But what about every other one, starting with the odds? Well, I have 1, 2, 4, 8, 16. These are all powers of 2, going up by 1 power each time. 16 is 2 to the 4th, so I'd expect my next one to be 2 to the 5th, or 32, and 2 to the 6th, or 64. Okay, next. Okay, we're going up. We're not hitting every integer. These are not powers. So a good thing to do at any time when you have gaps like this, or you're increasing or decreasing, see if we have a common factor, or a common ratio, or a common difference. Well, in this case, I certainly don't have a common difference. Difference of 3, difference of 6. Out here, this is a difference of 9. I mean, there's a big difference. Okay, but I do have a common ratio. I can multiply by 2 in each case. So whichever number I have, multiply by 2, I multiply by 2, that gives me the next ones. So after 192, I'm going to have 384. Times 2 is 768, and times 2 is 1,536. Okay, next sequence. Well, this is a decreasing sequence. It's steadily going down. In this case, if I look at my difference, I do have a common difference. I'm subtracting 7 each time. So I go from negative 20 to negative 27. After that, I'm at negative 34. Negative 41, and negative 48. Okay, my next sequence. Again, I'm increasing this time. Don't have a common difference, but the differences are interesting. From 3 to 5, that's a difference of 2. 5 to 8 is a difference of 3. Difference of 4, 5, 6. The gap is increasing by 1 each time. So if my gap between these two was 9, now let's do a gap of 10. That'll get me to 57. A gap of 11 takes me to 68. And a gap of 12 puts me to 80. Okay, 2 more. My next sequence, 2, 16, 54, 128. Okay, anytime a sequence gets very large very quickly, 2 good things to look at. 1 is to see if you can find any powers, something being raised to a power here, or a factorial. Both of these will increase numbers very quickly. Factorial, the most. So if you have a very rapid increase, definitely look at the possibility of there being factorials in place somewhere. Okay, so let's take a look at this one here. 2, 16, 54, 128. Not very clear powers. These are not perfect squares. These are not cubes or anything like that. But what we do have, 16 is 2 to the 4th. 2 is 2 to the 1st. So I have increased by 8. Can I multiply each term by 8? No, that doesn't quite work. How about this? Instead of 2 cubed, I can also write this as 2 times 2 to the 3rd. Okay, 54. Can I make that 2 times something? Well, that's 2 times 27. 27 is 3 to the 3rd. So I have 2 times 2 to the 3rd, 2 times 3 to the 3rd. Is this 2 times 4 to the 3rd? Well, 4 to the 3rd is 64. Yes, it is. How about 2 times 5 to the 3rd? 5 to the 3rd is 125. Yes, these work. So it looks like that's going to be our pattern. So 2 times 6 to the 3rd, 2 times 7 to the 3rd. This would be 2 times 8, 2 times 9, 2 times 10 to the 3rd. So doing that out, 2 times 8 to the 3rd gives me 1,024, 1,458, and 2,000. Okay, last one. These numbers get enormous. By the time I'm at the 8th term, I've gone from 2 to 40,000. This is almost assuredly a factorial in some way, shape, or form. So let's just write out what some of our factorials are. Maybe we can do a comparison. The first few should be fairly easy. 1 factorial is 1. 2 factorial is 2. 3 factorial, 2 times 3 is 6. Times 4 is 24. Times 5 is 120. Times 6 is 720. So those are a couple good ones just to start with. After that, a calculator helps. Well, if you compare the numbers in our sequence, they don't match these, but they're very close. In fact, each number is 1 bigger. So it looks like I'm going to take a factorial and add 1. So 1, 2, 3, 4, 5, 6, 7, 8. This should be 8 factorial plus 1. If you put that in your calculator just to confirm, you'll see that that is correct. This is indeed 8 factorial plus 1. So I'll want 9 factorial plus 1, 10 factorial plus 1, and 11 factorial plus 1. And doing those out on your calculator gives you 362,881, 3,628,801, and 39,916,801. So those are all of the sequences, a simple rule for each, plus their next 3 terms.